Hello everybody, Adam Lusick here, and with the release of things like ModernBERT, I thought it would be good to take a step back and highlight the BERT models, something that's actually been a crucial part of natural language understanding and deep learning for a while now. Essentially, there's kind of two approaches to natural language understanding. The first that are much more popular and well known are the decoder-based architectures that process language sequentially from left to right. Things like ChatGPT or the Generative Pre-trained Transformer, GPT, is considered a decoder. By sequentially, we mean that they're almost predicting each token, token by token. So as one token is predicted, then it re-ingests all of the last tokens and predicts the next, similar to what we're seeing here with GPT-4o. But on the other hand, we have things like BERT models, which are considered encoder models, where essentially, instead of doing this sequential token prediction, it's going to take the entire sequence of text that you have, or token IDs, which we'll get into in a little bit, and create a dense representation of that. If you work with language models and AI-based systems, you've likely interacted with encoder-based models through the form of retrieval augmented generation. They are what do the actual encoding of something like a passage or a document into this dense vector form that can then be put into a vector database and semantically retrieved. These models tend to be a lot smaller than our large many billion parameter decoder models like the GPT models, which makes them perfect for lightweight, highly customizable language understanding tasks, which is what we're going to explain in this video today. How these encoder-based models and the BERT architecture is actually set up, a little bit of why it's been important over the last 6 or 7 years of artificial intelligence, and what makes it so good and so popular for different downstream NLU tasks. Then closer to the end, I'll show you how I use the latest ModernBERT release to actually train a classification model. To start, BERT stands for Bidirectional Encoder Representations from Transformers. And what makes them different from the sequential token-to-token prediction models that we see with large generative language models is that what they do is they take in the full sequence, so entire words or sentences or documents, and then they return back rich representations of that. What you mean by this is that each word, as well as the entire phrase, is going to be converted into numbers. And these numbers are going to semantically capture all of the features of that sentence. That sounds a little bit confusing, but essentially what we're able to do is convert words into numerical representations. And then these numerical representations, which are literally just going to be lists of numbers, are going to represent what the actual meanings of these words in the sentences, as well as the whole phrase, means. So it's able to capture all of the understandings of language into numbers, which is great for mathematical or machine learning algorithms that then use this understanding of language in numbers to do all sorts of different processing tasks, like generate text with our GPT models. It's based on the very popular transformer architecture, which essentially uses a concept called attention. And what attention does at a high level is it allows the machine to understand how each word actually relates to others in a sentence. So through its training, it's able to see that words like interest in this case, in this sentence means kind of, understanding or care about, but it could also mean interest as in percentage when related to the bank's interest rates. And so the attention mechanism allows these very minute interpretations of word meanings by looking at how these words might actually be used in a sentence. So in this sentence here, interest is more related to hearing or having no interest, which means kind of like, how much you would like something, whereas interest in this second part is more related to rising rate and bank, which then we understand is more the percentage interest rate. So through using this concept and exposing these models to a lot of text and language as it's being trained, they're able to develop these machine-learned understandings of natural language. And as we mentioned, being able to understand natural language is very useful for multiple downstream tasks like named entity recognition, question and answering, embedding models for search and retrieval, and a few more that we'll take a look at. You're probably wondering then, if we're able to know the relationships between words in a sentence using this attention mechanism, how then do we actually do the training and learn language? Well, the original BERT paper from Google introduced the idea of masked language modeling. Essentially, showing the language model a sentence but with one word removed, and then having the model predict what word might go into that. So, for this example of how our mask doing today, you and I would likely know that we would probably say, "How are you doing today?" And this is exactly the same process that these BERT models are doing. Except in this, it's very algorithmic. So as it does a prediction, it's checked whether or not that prediction is accurate or not. And then, of course, its underlying neural networks, weights and biases are update to get it more close towards actually predicting the right word. This is also where the bidirectional part of this encoder model comes into play, because as you can see, we are using all of the words in a sentence, both to the left and to the right of what that mask might be, which is bidirectional, to actually do its prediction. And through doing this process across many, many millions and billions of words and sentences and phrases, we're able to machine learn an understanding of language through doing these predictions. About 3.3 billion words actually have contributed to the training of the original BERT model, around 2.5 billion from Wikipedia, and then Google's book corpus, which is about 800 million words. But not only did they do this masked language modeling, at the same time in the original BERT model, they also had another objective function of next sentence prediction, essentially putting together two sentences sequentially and having the model answer whether or not they would be sequential sentences. And so after all of this large-scale training, through all of these fancy techniques like the transformer attention modules and whatnot, at the end of the day, what Google was able to do is create this BERT model that had a very robust understanding of natural language. The two main benefits then at the end when they had this model that had been trained on natural language understanding is first, it was incredibly lightweight at just 110 million parameters, which at the time was actually quite large, but in comparison to some of the many billion or trillion parameter models now is very small. It was very small and able to run very quickly on not a lot of hardware. And then secondly, and likely most importantly, is that with a very strong natural language understanding base model, fine-tuning it for other NLU-based tasks became very easy, as you could take advantage of all of the hard work that's already been done to instill natural language understanding into the model and just do some slight tweaks for whatever task you need. And train people did. BERT models and encoder models are still some of the most downloaded ever on platforms like Hugging Face, with things like BERT Base Uncased having 61 million downloads last month, as well as many thousands of fine-tunes. With a small, lightweight model like this, you can fine-tune it for things like sentiment analysis, spam detection, even things like question and answering, as all sorts of different classifiers, a whole lot of anything that you would need that requires understanding natural language. The way that something like sentiment analysis would actually be fine-tuned for is the original model, when you input in a sentence, will for each word of the sentence output essentially what's a list of 768 numbers. And within those 768 numbers, it attempts to capture the meaning of the word in that sentence, but then also one extra classification class label. This is going to represent your entire document or sentence. So for something like classifying whole sentences or doing something like sentiment analysis, all you would have to do is add one extra layer that looks at this full sentence classification and the representation of it, and then train with some training data to be able to accurately take this class label and say whether it's positive or negative. Also similarly, as I mentioned, each word in a sentence will have an encoded number in it, and what you can do is actually take all of these individual numbers and then use them for something like named entity recognition, where from a sentence you extract out and classify each individual word. Or for something like question and answering, you could input a question and then a special separator and then your document, and train the model with its understanding already to be able to predict where the start and end of the answer to your question is in the sequential document. So really, this versatility through very simple fine-tuning explains BERT's practical impact. It has quick adaptation to new tasks, minimal training data needed compared to training from scratch, and then strong performance from leveraging pre-trained understanding. which explains a lot about why BERT models are some of the most used, most downloaded, and most in production natural language based models out there today. You likely interact with BERT models every single day as they're popularly used with the Google search platform for finding the specific parts of searches that are more relevant or related to your actual question. Really, at its core, BERT models have become some of the most efficient and lightweight ways for applying different natural language understanding tasks. So while GPT models can do a lot of what these encoder only models can actually do as well, they come with a lot of downsides. Namely, they're much larger, harder to serve, they cause a lot of latency and cost a lot. For example, the FineWeb dataset, which is 15 trillion tokens of filtered down web common crawl data, went through a filtering step actually using encoder models. And from this blog post, if we do some back of the napkin math for 15 trillion tokens, if you were to run something like a fine-tuned BERT-based model, it would cost about $60,000 for 6,000 H100 hours, which on the other hand, if you're running 15 trillion tokens through things like even Gemini Flash, which has a very low inference cost, it would cost over $1 million. So BERT models have remained incredibly popular, well used, well fine-tuned, and in production today. But there has been one interesting downside to this. There is one thing that you can actually probably have noticed, is that with the massive investment and building of different models, decoder-only models have gotten a lot more love than encoder models. With different advancements in large language models, which this graphic doesn't even capture past much of 2023, coming pretty much, every week, if not every other, there's been a lot of advancements here. However, the encoder-only branch over here has not seen the same amount of growth, with some of the latest models that are still being used being as old as around 2020, 2021. That is until late December 2024 when the Answer.ai and LightOn team released ModernBERT. And so they aim to actually bring all of the applicable advancements in language modeling from things like large language models back over into encoder models, making a modern and updated BERT model that can be used as a slot-in replacement for traditional BERT models. I won't go into the nitty-gritty technical of how each one of these advancements actually works, but rather I'll list them out and explain a little bit about it and have additional readings in the description below. But to start, one of the main things that they do is upgrade the transformer that is the kind of backbone of the BERT model with a few specific advancements. Most notably is rotary positional embeddings. ROPE better handles the actual positional embeddings or understandings of how tokens relate to each other across varying lengths or longer sequences. So this enables their ModernBERT model to scale up to an input size of over 8,000 tokens, whereas regular BERT models before this that weren't using the rope positional embeddings actually only allowed about an input of 512 tokens. They have a few more specifics at the individual layer level, so for all the multi-layer perceptron layers that they have, they've replaced them with generalized Gaussian linear units, removed unnecessary bias terms, and added some extra normalization layers after embeddings. They also implemented alternating attention, whereas before there was generally global attention in every single layer, so all tokens attend to all other tokens. But now what they do is every third layer is global attention, and then they have local attention with a 128 token context window for the others. This approach matches more specifically how you and I would kind of pay attention to the text in a document. We don't necessarily need every single word in there to understand the meanings of some. And they've made a big emphasis on diversity of training data. So ModernBERT's trained on 2 trillion tokens, but most of it is actually unique. Standard practice is usually to use the same training data over and over to get the most out of it, but they went the extra mile and created this data set of all unique data. And more notably too is that they included some kinds of data that weren't originally in the original BERT model training things. More specifically, things like code. They have a lot more nitty-gritty, more technical things that they do better than the old style days, but they also remove the next sentence prediction objective as well, only using the masked language modeling. All of this attention to detail and updating really paid off for the team because the release maintained, if not improved, on a little bit of the efficiency of running the model and had an across the board improvement on all of the things that BERT models are measured on. So, this really opens up the next era of encoder based natural language understanding, modeling, and building. And a big kudos to the team as they've released pretty much all of their model as well as different checkpoints along the training process, fully open source for folks to check out and use. On that topic of using, let's actually show how you can fine tune ModernBERT for a classification task. I've gone through and trained their large version for language model routing, essentially taking in a query and returning back whether a small language model or a large language model should be able to answer it. Before I start, I would like to give full credit to Philip Schmid here, who is an incredible machine learning researcher and I believe employee at Hugging Face, who put out this blog, Fine Tune Classifier with ModernBERT in 2025, where pretty much most of the code and methodology for what I'm about to demonstrate comes from. So to start, we have our candidate model, which is of course going to be ModernBERT. I chose to do ModernBERT large because Philip just did the ModernBERT base and wanted to see if there was any difference with the large model myself here. And then we need our candidate for what we want it to do. And as mentioned, it's going to be LLM router classification. So there is conveniently a nice large data set of about 15,000 rows from Dev Kassar here, the LLM router dataset synth. This contains about 15,000 rows of prompt and labels. So these prompts are just all going to be regular prompts, and then the labels are going to be either 0 or 1, which 1 in this case is going to be large LLM, and 0 in this case is going to be small LLM. So after installing the necessary packages here in this first cell and then doing the regular logging into Hugging Face with this, what we need to do is prepare our data set. So as mentioned and just shown, we're going to be using the LLM router dataset. And what we can do is use the Hugging Faces datasets package to load this. So from our ID, we call load dataset to download and load the dataset. We can then split that into both our training and our test set by just adding on this key here. In doing that, we see that our training dataset is about 15,000 entries and our test dataset is about 5,000 entries. So more than enough data to effectively teach a classifier how to do this. We then need to just make sure that our dataset is in the right format then for training. And the Transformers library trainer, which is what we're going to be using, expects just 2 columns, one marked labels and one marked text. So what we can do is use the remove columns and rename columns in a few sequences like this, so that finally at the end of it, we get our data set here that has just text and labels and the number of rows. But actually, we're not going to be working with the text directly. We're going to do a little bit more pre-processing and convert the text into token IDs. Tokens are, of course, going to be the underlying ways that things like BERT or language models actually process text, and it's essentially a numerical representation of a piece of text, usually a little bit more than a word. Essentially, what these models rely on is compressing down language into these numerical representations by essentially having a big lookup table, where when running a piece of text through a tokenizer, it returns back all of the numbers that represent that piece of text. Those numbers are then usually what goes through the processing, as of course math is easier to do with numbers, and then our models re-output token IDs, which are then mapped back to the words that they represent back through the tokenizer to turn it from the machine understanding way of tokens back into words that we can read. So what we're going to do is load the tokenizer from ModernBERT, and then all we do is run all of the text through our tokenizer to convert it into these tokens. We set a max length of 1024, which means that all of the queries are going to be 1024 tokens. If they are not 1024 tokens, then special padding tokens will be added to the end to make them up to 1024. So when running that through our data set on both our test and our train, What we get back now is that for each of them, we have our labels, which are going to be the 0, 1, representing either a small or large language model, our input IDs, which are going to be our token IDs, as well as an attention mask. The attention mask in this case is going to actually come into play if one of the inputs did not reach that 1024 tokens and thus had the padded tokens added to it. It is going to show the model during training what's actually just the text and then what's just the padding so that it doesn't have to do any of the processing on the extra padding, but it still maintains this maxed length across everything so that it all runs efficiently. A quick pseudocode example here. If we have the text hello world, we'd run it through a tokenizer and then it would look something like this, where we have a special beginning of sequence, or the classification token in this case, and then the specific numbers that represent hello and world, as well as a separator, and then a bunch of zeros for the padding to reach up to 1024 tokens. Our attention mask then is just going to show that all of the actual useful data here, from the classification to the end padding, is in these first 4 positions, and then the rest are just pads. Our labels then are going to be either 0 and 1, since we're doing binary classification between small and large language models. So now with our full data set ready, what we need to do is prepare our model. We're of course going to be using still our transformers package, and what we're going to be doing is preparing the ModernBERT large model with their auto model for sequence classification function. What this is going to do is take our base model and then add a classification head onto the end. This is very similar to what we were saying about using the power of the base BERT models, but then fine-tuning them with a few different tweaks at the end. Essentially for classification, what we're going to be doing is adding one final step where the output of the model is going to run through a layer or two, and it's going to do the prediction of either 0 or 1. So we pass in the model as well as the number of labels, which is going to be 2 in this case, and the label to ID and the ID to label dictionaries, which are going to look a little bit like this. So at the end of it, what this is going to do is initialize our model, but it is going to say that not all of the weights are actually initialized from the checkpoint, and some are new, essentially the classifier section here. This is going to be the main part of what we're actually going to be training. And it duly says you should probably train this model if you've initialized it like this. So perfect. Now that our data set's ready and our model is ready, we need some form of actually evaluation metric to assess our performance against. And what we're going to be doing is using the F1 score. F1 score combines precision, which means that out of all the times that we actually predict large language models, how many of these were actually for large language models, as well as recall. And recall is going to be, out of all of the actual large language models in our set, how many did we catch? So our function here for finding the F1 score is going to actually take in our raw output probability, which is going to show, given an input, the probability of it being either a 1 or a 0, which is going to be either a large or a small language model, use an argmax, which is going to select the class with the highest probability, and then calculate our weighted F1 score. We're going to be using weighted F1 scores to account for all of the classes and whether or not it's actually balanced, which means that there might be more entries that have small LLM or more entries that have large LLM, and it'll take into account all of this when running these scores. So we'll be calculating this during our training to help us understand how well our model is actually learning. Thus, now with our dataset, our model, as well as our training evaluation metric, what we need to do is just simply train the model. So once again, we'll still be using transformers and pass in some training arguments to a trainer. I won't go over all of the individual hyperparameters here that have been chosen. Most of them were copied from good old Philip Schmid's blog over here. And also I saw that they had some comparisons to the original BERT paper. But essentially what we're going to be doing is running across 5 epochs of our training data. So it's going to go through and train across all of our data 5 times. It's going to evaluate against our metric every single epoch, so that will be 5 times. And then what it's going to do is, of the 5 epochs, it will save the best 2. And it's going to determine this best through evaluating, of course, our F1 score. So with a few more of these technical details out of the way, we pass in our model, the arguments, as well as our different training and evaluation data set, and our metric to the trainer, and we run it off. So on this L4 GPU and the collab notebook that I'm using here, it took about 11.5 minutes to do the full training. And so you can see across all of the epochs that our training loss is decreasing and our F1 score is increasing. So with what appears to be a successfully trained model, what we can do is create a quick card, save it, and push it up to the hub, which is where it sits today if you're interested in taking a look. But let's actually load it then and run a few examples through. So using Transformer's pipeline helper, we're going to create a text classification pipeline and pass it through our model ID. So this will download and load the model and put together everything we need for a classifier. So after the 1.5 minutes or so it took to load that, what we can do is run through some predictions. So for our first sample, we're going to pass in this quite complicated biology, I think, related question that I kind of asked Claude to make for me. And what we're hoping for is to see it output that it should be a large language model. And that's what we see. And then on the other hand, if we ask a very simple question like, why is the sky blue? We should hope to see a small language model. A little bit quicker there, and we see small LLM. So we can say with confidence that this actually works and that our training was successful. That being said, I hope this video gave you some appreciation and insights into BERT models, as well as some practical ways that you can start using them yourself. I'll have all of the resources and more linked in the description below. And if you like the video, leave a like on the video. If you have any questions, leave them in the comments below. And if you want to see more like this and support the channel, consider subscribing. Thank you and have a great day.